Right. So by now we have discussed so many concepts in quality control, right? That is, we have discussed about the OC curves and we have discussed about the statistical control charts. So in this session also we are going to discuss furthermore about the OC curves and about the acceptance quality level, about the lot tolerance percent defective, and about the different types of OC curves, right, and the behavior of OC curves when C value is equal to 0, and also how to design single sampling plans. So as we have discussed in our previous sessions, we know the acceptance quality level, or the AQL level, that is the poorest level that a consumer would like to accept a lot, right? And then again we discuss what is lot tolerance percent defective. That is again, when it comes to LTPD, that is the poorest level of quality that the consumer is willing to accept when you consider an individual lot. Right? So in this case, there are two types of OC curves, because we know when you draw the OC curve, what we simply do is you have a lot and you take a sample and you count the number of defectives in the sample. If the number of defectives in your sample is less than or equal to the predefined C value, we are going to accept the lot, or we are going to, in the other hand, we are going to reject the lot. So in this case, if you take a whole lot and if you know the proportion of the defectives that you have in the whole lot, you can apply the binomial distribution equation in order to calculate the probability, right? So that's what we have discussed in the last session. So in that case, if you are going to apply the binomial distribution, when you draw the OC curve, we know in your x-axis in the OC curve, you have the percentage or the proportion of the defectives, and your y-axis would be the probability of accepting your lot. So in that case, if you have calculated those probabilities using the binomial distribution, we call it as a type BOC curve. But if you think about a whole lot, we have defectives, we have non-defectives, right? So it's like, if you know the size of your lot, let's say you have 1000 units and there you have 100 defectives and 900 non-defectives, and if you are going to take a sample of 50, your sample also would be a sample also consists defectives and non-defectives. In that case, since we know the lot size, you can apply the hypergeometric distribution as well to calculate the probability of having one defective, two defectives, or zero defectives, right? And then you can calculate the probability of accepting the lot. So if you have used the hypergeometric distribution in order to calculate the probabilities of the OC curve, we call it as a type AOC curve. But if you take the same data set and if you plot type A and type B OC curve on the same graph, you will see all the time type AOC curve will fall below the type BOC curve, right? That is, from the hypergeometric distribution, you get a less probability compared to the binomial distribution. And the next thing is, what will happen if the OC curve, when you draw the OC curve, if the C value is equal to 0? So what does that mean? So in the single sampling scheme or in the acceptance sampling scheme, if C value is equal to 0, that means we are going to accept that particular lot when we have 0 number of defectives in our sample. So actually that is a very rare case, right? That is, our sample is a perfect one. So if that is a very rare, the probability of having such sample is something very rare. The probability is very low. So because of that, when you draw the OC curve with C value equal to 0, you will see an exponential decrease with P. right? Because when the probability of the P means the percentage of the defective. So when the percentage of defective is very high, to accept a lot with zero number of defective is something very rare. So the probability is very low. So that's why when C value is equal to 0, when you draw the OC curve, you will see an exponential decrease. Alright, so the next thing is, how are you going to design a single sampling plan using a OC curve? Right, so the first thing is you have to select any 2 points in the OC curve. So I will show you this one. So I have included a handwritten sketches. Now if you can see, this is the OC curve. The first step is you have to select any 2 points, right? So let's say from your x-axis, that is the proportion of the defectives, I have selected P1 value. So the corresponding Y value, that is the probability of accepting that lot when you have P1 proportion of defectives in your lot, right? So that is accepting probability. I have taken it as AP1, and the next value is P2, right? So again the corresponding probability is AP2. Alright, so when you take these values, in this case what you can do is, we know if now just imagine when you draw this OC curve, you have used the binomial distribution, that is it's a type BOC curve. In that case, if you want to calculate this accepting probability, and if your P1 value is known, you can use binomial equation, that is NCX P to power x 1 minus P to power n minus x. That is the binomial equation that we use to calculate the probability of acceptance. So what we do is, I'm going to take these two probabilities, that is the probability of accepting the lot when the percentage of defective is equal to P1. I'll take this point as A, and this point, that is the probability of accepting when the percentage of defective is equal to P2, as B. So I have 2 points as A and B, right? And then now, since we are using this binomial equation, we have no idea about n and c. So I take the binomial equation where x goes from 0 to c, and I have no idea about n. So in the first coordinate, the percentage of defective is equal to P1. So I can substitute P1 for P here. And then this probability of acceptance, we know the value, that is A. I can do the same thing for the second one, that is n value and c value are unknown. So you can take P value as P2. So P2 into power x 1 minus P2 to power n minus x, and this probability we know that is equal to B. So there are two unknowns, n value and c value. We do know, but we have two equations here. So what you can do is, you can just solve these two equations using a numerical method, or you can substitute n value and c values to the two equations until the right hand side and the left hand side get equal values. So in that case, you can find the corresponding n value and c value for your sampling plan. But you can see this is very time consuming. So what we do here is, actually there is a graph where you can easily find the values for your single sampling plan using this graph, right? So before going to the graph, actually what we do is, when you take this percentage values, as a standard, we take the P1 value as AQL and P2 value as LTPD value, right? And then when you take P1 as AQA, simple A means the probability of accepting your lot at AQL. So that is, you can take it as 1 minus alpha, and B value means the probability of accepting your lot at LTPD. So you can take it as beta. Alright, so let's say you are given that your p value, AQL value is 0.01 and 1 minus alpha value is 0.05, and then your p value, the LTPD value is 0.06, beta value is 0.1. Right? So in that case, what you can do is, right, in your graph, I'll show the graph here. You can see on your left hand side you have some probabilities, and again in your right hand side there's another scale with probabilities, right? So what you can do is, first you can, the LTPD value and the AQL value you have to mark on this first scale, which is on your left hand side. Then 1 minus alpha and the beta values you have to mark with this, that is the probability of CO fever occurrence in N trials. With this probability scale you have to mark it here. Right? So as for an example, if you are going to mark the AQL value 0.01, you can mark it here, and 1 minus alpha value 0.95, you can mark it here, and then you can take LTPD value, if it is equal to 0.06, you can mark it here, and then you can take beta value 0.1, you can mark it here. So at the intersection point you can read the value from the graph. That would give you your N and C value. Right? So if you look at this one, see, if your AQL value is 0.01, you can find it here, and let's say alpha is 0.1. Right? So if alpha is 0.1, you can take 1 minus alpha as 0.9, so that is 0.9 is somewhere here. So you can join these 2 points using a straight line, and let's say LTPD value is 0.05, it's somewhere here, and let's say beta value is 0.1, it's somewhere here. So you can join those two values as well, and at the intersection point you can see here in the graph, these are the occurrences, C values, and these are the sample size values. So at the intersection point, if you read, you will get the sample size as 110 and the C value as 2. Right? So I think up to that point, you are clear with the OC curves, and you are clear with the differences between those C curves, what happens when we change the C value, when we change the percentage of the defective, and when we change the sample size, and what are the differences between the type A and type B OC curves and all. Right? So furthermore, we are going to discuss about assessing the quality of a given process using some values, right, using some measurements. So in that case, the first thing we are going to discuss is the average outgoing quality. So when it comes to the single sampling plans, this average outgoing quality is something very, very important. So average outgoing quality means on average it measures the outgoing quality of your given lot. Right? So in this case, in order to measure this average outgoing quality, we use this formula, that is, you can see PA times P into N minus N over N. So in this case, capital N is your lot size, simple N is your sample size, and then you have simple P. So simple P is the proportion of the simple P is the proportion of the defectives, and PA, that is the probability of accepting a lot with the proportion of the defective is equal to simple P. So in this case, what would happen is, now first imagine your lot size is very large. Right? So when you compare your sample with the lot size, if it is very, very large, we can take N minus N, this term, as equal to capital N. So that is capital N divided by capital N would be very close to 1. So in that case, if your lot size is very large compared to the sample size, average outgoing quality is equal to PA times P. That is the proportion of the defectives you have to multiply by the probability of accepting, right? And then what will happen if P is very small? That is, the proportion of the defective is very small, means you have only few defectives in your lot. So if you have very few defectives, there is a higher chance to accept that kind of a lot. So that the probability of acceptance is very close to 1. In that case, if you take the AOQ equation, PA is very close to 1. So the average outgoing quality you can write as P into N minus N over N. Right? So what would happen if P is very large? That is, you have the proportion of defective is very large. You have so many defectives in the lot. So if you have so many defectives in the lot, you have a higher chance to reject that kind of a lot. Right? So that is, accepting probability is close to 0 because there is higher chance to reject that. So if PA is close to 0, that is, this whole term would be close to 0. That is, AOQ is close to 0. Right? So that is what you have to remember is, when P, the proportion of defective, is close, very small, the P AOQ you can calculate using this equation, and when the proportion of defectives is increasing, AOQ is very close to 1. Right? Because when there are so many defectives, when you calculate the average outgoing quality, it is close to 0 because actually there is no quality when you have so many defectives. So in order to demonstrate this one, I have taken this example. So you can see our lot size is 1000 and I'm going to apply the simple single sampling plan where I'm going to take a sample of 50 units and where the C value is equal to 2. Right? So in that case, if we are going to calculate the probability of accepting the lot with the given defective proportion, you can use the binomial equation. Since the C value is equal to 2, when we calculate the probability of accepting, what you have to do is probability x value is less than or equal to 2, given the p value you have to calculate. So what I have done here is, now I have taken different p values starting from 0 0.01, 0 0.02 likewise, and in each case I have calculated the probability of accepting each lot with the given proportion of defectives, and then I have substituted here I have taken this equation, and then you can substitute the PA value and the P value to the equation, and you can find the corresponding AOQ value. So I have the PA values, AOQ values and the P values. So what I'm going to do is, I'm going to take the P values to my x-axis and take the AOQ values, that is the average outgoing quality values, to my y-axis and plot a graph. Right? So I'll give you 1 minute. Right? Just give a try and see whether you can plot it. Just take the probabilities to your x-axis and the AOQ values to your y-axis, right? And just plot AOQ values and P values and see what will happen. Just a rough sketch would be enough. Right, so I'll show you my graph. So you can see for the x-axis I have taken the proportion of the defectives and my y-axis is the AOQ values. So as we discussed, you can see when the proportion of the defectives are increasing, AOQ value is very close to 0. And if you look at the beginning of the graph, you can see an increasing trend and it has a peak point, a maximum value. Then again there is a decline, right? There is a downward trend. Okay, so in this case, if you look at this graph, this maximum point is something very important. We call it as the average outgoing quality level of a process. So if you have a process, you can just draw the respective AOQ graph, and when you find this maximum point, that will give you the average outgoing quality level. That is the maximum value of the AOQ, right? So if you look at, just look at this one, okay, so that is something close to 0.045. So actually when you compare the AOQ L value with the AOQ values, right, it's the maximum value. If you compare all the AOQ values, since we take the maximum AOQ value as the AOQ value, that is the maximum average outgoing quality, we call it as the average outgoing quality level. So that is all the other average outgoing qualities are less than or equal to average outgoing quality level, since it's the maximum value. Right? So since we are talking about the process, sometimes it is important to calculate the average total inspection as well. That is, on average, how many items that we have to inspect. Right? So that one we can calculate using this equation, that is n into probability of accepting plus capital N into 1 minus probability of acceptance. So you can rearrange the same equation like this, right? If you simplify this one, right? Okay. So in this case, if you just substitute the values for the above example, right? Here the capital N value is 1000 and the simple N value is 50, and if you take here, right, and if you take in this case, see, the simple N value is 50, capital N value is 100, N is 50, 1 minus, let's say when P is equal to 0.01, right, P is equal to 0.01, PA value is 0.98. So you can substitute PA as 0.9862. So in that case, if you substitute these values, you'll get the answer as 63. That is, for this particular process, on average, we have to inspect 63 items. Right? Okay. So in this case, we can again check what will happen if you draw a graph with the proportion of the defectives with the ATI value. So these are the ATI values and this is the proportion of the defectives. You can see when the proportion of the defectives are very high, what we have to do is we have to, on average, we have to observe so many items. That is the ATI value, the average total inspection value is increasing when you increase the proportion of the defectives, right? That is very clear in this case, you can see it. Right, so if you graph it also, you can see it very clearly, because in this case, when you increase the proportion of the defectives, you can see the graph is showing an increasing trend because the ATI values are also increasing. right? Because actually what happens in the quality control field is, now initially if you have a plan, like if you are using the single sampling plan, we are going to have a sample of 50 items. But if you have so many defectives inside that 50 items, sometimes we just we are going for another sample, or sometimes we are going to take some more random values and check what will happen with those random values, right? So that's why when you have so many defectives, we tend to observe, or we tend to inspect more values from a lot. So when you have more defectives in your lot, the average total inspection is also increasing. Right, so when it comes to designing a sampling scheme, if you now in previous slide we discussed how to design a sampling scheme when you have the AOQ value, and when you have the LTPD value. Based on those values, the use of alpha and beta, how can we design the sampling scheme? So in this case, if you are asked to design a sampling scheme by giving the AOQL value, that is, if you know the average outgoing quality level, and if you are asked to design a sampling scheme, that is not possible, because to design a sampling scheme, we need to have other information as well. The AOQL value is not sufficient to design a sampling scheme. So what we do is, all the time when it comes to a process, we have to try to minimize the ATI value, that is the average total inspection. That is, all the time we have to minimize the number of items that we have to inspect, right? Because it's time consuming and it's very costly, so we have to minimize the number of items that we have to inspect for a given P and for a given AOQL value, that is for a given proportion of defectives and for a given average outgoing quality level. We have to minimize the number of items that we have to inspect, right? So in this case, actually when you look at a process, the very crucial value is the proportion of the defectives. That is something very important, because we observe the graph of AOQL versus the proportion of the defectives, and the graph of ATI versus proportion of defective. In both cases, we observe how it's changing when we change the proportion of the defective. So that is a very crucial point. Alright, so the other thing is, then again, in order to measure how stable is your process, we can use the process capability index. In the process capability index, it always measures the uniformity of the process, right? So that is, at a given time, how good your process is, whether it's stable or not. So using this process capability index, you can get an idea about your process. So if you are asked to calculate the process capability index, you can use this equation. That is, when you take the difference between your specification limits, that is the upper specification limit and the lower specification limit, then you have to divide it by 6 sigma, since the difference between since we are talking about the 6 sigma control charts, we know the difference between the upper control limit and the lower control limit is equal to 6 sigma. So you take the difference and then you have to divide it by 6 sigma. And we know there are special cases where you have no lower limit and sometimes you have no upper limit. In that case, when you want to calculate the capability index, you can use these equations. That is, if you have no upper limit, you can replace the upper control limit or the upper specification limit value from the mean, right, and take the difference between mean and the lower control limit. Since that difference is equal to 3 sigma, you can divide this by 3 sigma. And then when there is no lower control limit, what you can do is you can replace the lower specification limit value or the lower control limit value by mu. And since again that difference is between the upper specification limit and the mean is equal to 3 sigma, you have to divide this value by 3 sigma, right? So in this case, when you calculate the process capability index, what we do is we always check whether our process capability index is greater than 1 or it is less than 1. If it is greater than 1, that is we are in a safe situation, we have nothing to worry. But if it is less than 1, that is it will give you a warning signal that your process is in a bad position or there's something wrong with your process. So then we have to stop your process and find out what are the assignable causes and the root causes for this warning signal, right? So actually this process capability, by calculating the process capability index and by checking whether the process is in control, it's stable or not, that is something very important, and that is something we widely use in the statistical quality control field. So actually we call this as the process capability analysis. So the process capability analysis, it's actually an engineering process because we estimate the process capability, and then in that case we check whether the process is stable or not using the probability distributions, right? So this is very important, the process capability analysis, because we can when we use the process capability analysis, we can predict how well our process is and how well the process will it will predict how well the process will hold the tolerances, and then it will assess product developers and the designers when they want to select or modify the process. And then if you want to change the intervals between the sampling, or when you want to change some process monitoring techniques, right, this process capability analysis is useful. Then if you want to use new equipments, right, and then you can use this process capability analysis also when, since there is a big competition in the industry, in order to survive in the industry, in order to compete with the other vendors, you can you always have to check the quality of your process. So in that case also your process capability analysis is very important. So apart from the process capability index, so I told you, I have mentioned in the slides that we are using the probability distributions when we do the process capability analysis. So actually the process capability analysis is not just measuring the CP value, right? So it's a huge process, but we are not going to discuss about that, right, due to the time constraints. But what you have to know is, when it comes to the process capability analysis, we'll be using histograms, we'll be using stem and leaf plots, we'll be using probability plots, right? Using these things, we can identify the probability distribution of your given process, and then we can take the necessary actions in order to keep your process stable, right? So So the process capability ratio or the process capability index. So this is the general format you can see. First you take the difference between the upper control limit and the lower control limit and you divide it by 6 sigma. But in the special cases where you have no upper control limit or no lower control limit, you have to apply necessary, you have to replace the upper specification limit or the lower specification limit by mu, right? And then for a given process we can calculate the percentage of specification band. So that is what we do is 1 over Cp. Since it's a percentage, you have to multiply that by 100%. So first you calculate the process capability index or the process capability ratio, and then you take 1 over Cp, and when you take the percentage of that, it will give you the percentage of specification band. Right? So I think so using these measurements we can always measure the stability of a given process. So we discuss so many things. So starting from the history of the statistical quality control, then we discuss about the philosophies, then we discuss about the concepts you have, and then we discuss about the different types of control charts, right, and about the OC curves and the acceptance samplings, and then we discuss about the process measurement criteria such as the AOQL and AOQ, AOQL and CP. So I think everything is clear, but we will do more questions, right? If you have any question you can ask. You can send me an email if you have any question. Thank you so much.